Today we begin chapter 4. It's not a really long chapter. And what we're going to be doing is looking into, we've developed this machinery for piezoelectric material. We're not going to talk about the material itself and get a little bit more into the physics of the material in this chapter. So piezoelectric, we're going to be focusing on piezoelectric. There's probably going to be an analogous piezomagnetic chapter, I think. So piezoelectricity occurs in a number of crystalline solids. Okay, now a crystal is something that has a approximately regular array of atoms or molecules. So it has, well, there are isotropic crystals, but in general there'll be directions, particular directions, and things will look different in different directions because of the structure. And what happens is in some of these crystals there can be molecular atomic asymmetries that lead to a permanent dipole moment. Okay, so here's a real simple example right here. You can see that think of this as a molecule. It's got this permanent electric dipole moment. And they're arranged in a regular fashion, the crystal here, a regular fashion. That's a very simplistic view, okay? What happens is, and you can see this, if you apply an electric, you have this crystal. If you apply an electric field, you're going to, it looks like, and what happens is here, you're going to stretch it. If you slap electric field on here. If the electric field goes the other way, and it's because, you know, the electric field puts an upward force on these positives and a negative force on the downward, so you're going to stretch it. If you flip the electric field, you're going to compress this. Okay, so that's half of the piezoelectric action right there. We see that an electric field can result in a strain or a change in the strain. Doesn't matter. It's not so obvious, but it works the other. I don't think it's obvious. It works the other way too. So here we see that an applied electric field can strain it. If we strain it, we change the electric field. So if you imagine compressing this, here, I don't think it's real obvious, but it's reasonable. I think it's reasonable. So this is, excuse me, this is just what we want for transduction, right? Now, as long as the actions here, the applied electric field or the stressing, is sufficiently small, this will be linear. So, and you know what that means. For example, if we apply an electric field here and we cause a strain, if we double the electric field, we get twice the strain. That's what linear means. So eventually, of course, at sufficiently large amplitudes, it'll become nonlinear. So somebody just asked me if the nonlinear course is being taught this spring, and I didn't think it was. Do you guys know? 4459?
I heard it wasn't.
Okay,
well,
yeah.
Not just from you.
Okay, yeah, it's the first time in 15 years or something. Apparently there's not enough student interest, so maybe the heyday of nonlinearity, you know, it was a really big deal. Chaos, all that stuff was intensely investigated. So my thesis was my dissertation was nonlinear, like a lot of other people in my generation. Maybe it's just not very popular anymore, I don't know. Okay, so, anyway, right, so that I got triggered by this. So there'll be a nice linear regime here. Now, I want to make sure you understand something here. you can have a piezoelectric material where the individual molecules or atoms have a net electric dipole moment, but they can be randomly oriented. Okay, so not in a regular fashion like that. That's a polycrystalline material, or also called amorphous. This is where they're just randomly directed. What's going to happen when you apply an electric field? Take a wild guess. Nothing. There's no strength. It's all going to average out. Okay, and the reverse is true too. If you compress it, you're not going to get any electric field. So that's not going to work. But there's a way, as we'll see, there's a way around that. All right. Now, incidentally, I don't know if we mentioned this before, but this comes from Greek, from a Greek word, piezo here. It has to do with the stress. So piezoelectric, as we've been saying since the first week, is, it's a combination of electric and elastic changes. There are naturally occurring piezoelectric materials, crystals, okay, that have been used in underwater acoustics. And some of them actually still are. Most of these have fallen by the wayside. Better materials have come along, as we will extensively discuss. But the primary example is quartz. Maybe you've heard of this. There's something called Rochelle salt, ADP, which stands for this, ammonium dihydrogen phosphate, lithium sulfate. I think this might still be used for some hydrophones. We'll do an example calculation of this later on in the course. And something called tourmaline. And as you might guess, each of these has advantages and disadvantages. So part of the game in transduction, particularly sonar transduction, is finding, a combination of geometries and materials that'll do what you want. And it's never perfect, right? It's all a trade-off. So we'll be talking, that's part of this course that we'll get into later. So historically, the use of piezoelectric material, one of its first uses was, guess what? War, okay, and submarine detection. It was done in France for World War I, and it was the goal was to detect submarines. This was by Langevin. There's a famous physicist, Langevin. I got a feeling there's more than one Langevin in history, okay? All I got to do is type it into Wikipedia, but I don't have the time, right? So if you do, let me know. I think there's several Langevins. Quartz is no longer used. It's got a low electromechanical coupling coefficient. The transduction is just not strong enough. But it has found use in what nobody has anymore, watches. What happened to watches?
On your phone now?
Yeah. Okay. So I guess, watches, they probably have taken a real dive, marketing of watches. Well, yeah. And this is kind of interesting. So it is used for accurate timekeeping. And I didn't know this, but it's got a high Q, which is what you want. Okay. But the problem is temperature dependence. If you're going to use it for a quartz crystal for timekeeping, you want it to be approximately the resonant frequency. I don't know the details at all. Okay, it's probably been driven by some feedback circuit so that it's driven on resonance. I don't know, but when the temperature changes, the resonant frequency changes, and that'll screw you up with the time as a timekeeping device. But it turns out quartz has quartz crystals have opposite temperature dependence. So if the temperature goes up, it may strain one way in one direction and strain the other way in the opposite direction in another direction of the crystal. So you can compensate for temperature changes to some extent. So that's kind of interesting, but it has found a home here for accurate timekeeping. Again, I should know more about this. Maybe one day I'll look this up. But what's going on there? How did they use a quartz crystal as a timekeeping device? You can kind of imagine stuff, but I don't know. But if anybody gets interested in this, you're looking at it, please let me know. Okay, drop by my office, let me know. I'd like to know. It's the time thing. Rochelle solder and ADP were also used in the early years of underwater acoustics. There's a little bit of a problem here. They're water soluble, so you have to insulate. Somehow you have to, insulate's probably not the right word. The technical term is pot. That's what people do, and we'll talk about that later in the course. You need to keep them separated. Isolated, separated from the water, right. And then another war, right? And we'll see this again and again. And it was the Cold War that really got all this going. And you can imagine why, right? Submarines carrying nuclear warheads parked off your coast. So there was a huge amount of effort in the Cold War put into sonar devices. But in World War II, it was discovered, barium titanate was discovered, and it's a ceramic. And this is a key thing. Almost all sonar material are ceramics, and we'll talk a lot more about that. But this was the first discovery, and so barium titanate is still used. But one of the things this did was, when it was found that ceramics could have very good properties, it opened up this door for all kinds of other ceramics. So that, and it got going, and then after World War II, when the Cold War came about, it just was in full swing. It was a huge amount of effort went into looking into sonar material, ceramic sonar material. Now there's another phenomenon here besides piezoelectricity. There's what's called electrostriction. It's a good word, and you'll see, you can maybe guess why. I'll tell you in a minute. It's appropriate. It's universal. It occurs in all dielectric materials. When you have a dielectric material and you apply electric field, guess what happens? It constricts, okay? And it's a typically weak effect compared to piezoelectricity. It's really not, it's too weak to be, by itself, to be useful in sonar. But we want to talk a little bit about it here because it arises. And what's happening here is when you apply, you have a material that has randomly oriented electric dipole moments, or it may not have. It can have dipole moments that we represent like this that are randomly oriented, or the molecules may not have a net electric dipole moment. But when you apply an electric field here, when you slap on a field here, you'll tend to I don't know how to do this. You can polarize this, right? And what happens here, and this is a mystery to me, but so when you apply an electric field, you will tend to orient these permanent dipole moments in this direction. You can also induce this, okay? The effect is the same, pretty much the same. You're getting a net electric polarization of the material. And what happens here is that there's an attraction between these positive and negatives, and somehow it causes a constriction of the material. If you can figure out how that does it, let me know. I looked into other books. I think I remember looking into Sherman and Butler. I couldn't find an explanation of it, but I'm sure it's out there. To get deeply into the physics here, my suspicion is you've got to go to a condensed matter physics book. It used to be called solid state physics, now it's called condensed matter, to really find out the physics here. But anyway, electrostriction, what happens is, and it's not obvious, because this electric field is going to tend to stretch the material, right? Once you've got these dipoles, you've got an upward force here and a downward force there. It's going to tend to stretch the material. But there's also an attraction, and somehow the attraction beats out this. So the tendency for the material to elongate here, as we were just discussing, gets beaten out by this attraction here. And it doesn't matter which, you're starting off with an randomly polarized material. It's an amorphous material. And it doesn't matter which direction you go. So if we look at the strain here as a function of the applied electric field, when the electric field, let's say this is positive, we get a constriction, a negative strain. So it goes off, it comes down to this quadrant. The same thing happens when you reverse the direction electric field. The direction, this is an isotropic effect here. Okay? So the strain as a function of electric field is going to have to look something like this. All right? And almost always in this case, there are a few exceptions in nonlinear oscillators, which you'll never know about because, of course, it's not going to be taught. This is quadratic here. This is a parabola. It could be quartic, right? It's got to have an even power. S has got to go like e squared or e to the fourth, okay, or e to the sixth. Usually, you can imagine a Taylor expansion. Usually in cases like this, it's quadratic. There are some interesting exceptions in nonlinear oscillations. So it looks like this. Why is this bad for us? Well, you know, what we want is a nice, it's weak, for one thing. It tends to be weak because it's maxing out here, right? So you don't get much strain. You get very poor electromechanical coupling here. For electric fields down in here, so that's one bad thing. And the other thing, it's not linear. It's inherently nonlinear. So this is no good. All right? However, suppose you have a ferroelectric material. Now you've all probably heard of ferromagnetic material. This is where you have, like iron. Iron atoms behave like a little current loop. There's a bunch of magnetic moments in there, and they don't all cancel. So in the end, an iron atom behaves just like a little tiny current loop that has a magnetic, so it's like a current loop. This will behave like a north pole. If this is in front of you, it's going like this. This is the north pole, this is the south pole. So an iron atom is like a little tiny magnet, a little tiny permanent magnet. And iron naturally occurring, they're typically randomly oriented. Now they can be influenced by the Earth's magnetic field. If the iron is molten and the electric field, they'll tend to align. And this is one of the ways people have been able to date things. They can see magnetization in iron and they can infer things. Geologists can infer things. But typically the iron is going to be randomly polarized. But then what do you do to turn it into a permanent magnet? You take this material, it's got all these the iron, it has all these randomly oriented moments, and you can zap it with a huge current, right, to create a magnetic field, let's say pointing this way, that will then cause these to align. Now, I didn't tell you an essential feature here, and I should have said this earlier. What happens is this net magnetic moment, and the reason I'm telling you this is the analogous thing happens in the electric case. Exactly analogous thing. These little iron atoms act like little tiny magnets, right? They're sufficiently strong that they can cause neighbors to perfectly align with them. So you end up with what are called domains. And these have very many molecules, but they're small on a macroscopic scale. So a hunk of iron can look like this, and they've actually taken pictures of this. It can look something like this, where this represents a domain where there's almost perfect alignment. I think it is like essentially perfect alignment of all the magnetic dipole moments. And then over here they could be pointing this way. Here they could be pointing another way. So here's the material has no net magnetization, but there are these little tiny domains here where you have perfect alignment. And when you apply a sufficiently strong external magnetic field, you can get all these things to align in the direction. How that happens is actually interesting. I believe the boundaries here actually migrate. I think Griffiths talks about this, but I can't remember. But anyway, the point is, you slap a sufficiently strong external magnetic field here in this direction, you're going to tend to cause alignment here. And now you have a permanent magnet. But this will come up in a few minutes. What happens if you heat the magnet? You keep raising the temperature. eventually there is an abrupt temperature. This is kind of interesting and I don't think obvious. There is an abrupt temperature at which the magnetization here, these are all now essentially pointing in the same direction, and in a typical permanent magnet there's almost 100% alignment. I think it's in the upper 90% of the alignment here. There's what's called the Curie temperature, and we'll talk about this in a moment. The Curie temperature, Pierre, not Marie, the husband and wife team, okay, where this disappears, it becomes randomized again. It's an abrupt temperature. So it's like ice melting into water. It's an abrupt, what we call phase transition. Okay, so what does this have to do with piezoelectricity? Well, when you have a ferroelectric material is material that behaves analogously as ferromagnetic material. You have these domains, and what you can do is you need to get them to behave as a piezoelectric material, you need to get these aligned. You need to get some alignment here so you don't have this problem right here. And this can be, there's two ways you can do this. You can permanently polarize the material, that's analogous to permanent magnetization. Or you can just externally keep an electric field on there. If you, I have trouble seeing this right now, but one way, not an unusual way to do it, is you need to bias this with an electric field. The standard way to do it is just zap it once, or I guess you could do it again, and I don't know about that, but it's just like a permanent magnet. You zap it with a sufficiently strong magnetic field. Here, if these this represents a ferroelectric, you zap it with an electric field and you permanently polarize it. And then, once it's permanently polarized, this is from Sherman and Butler. So here's a material that's been permanently polarized. That tends to elongate it, okay, in this case, for ferroelectrics. What happened to the electrostriction? They don't tell us. Okay, so there's little gaps here. But anyway, evidently here for ferroelectrics, the electric field, it tends to cause alignment of the dipole moments, and then there tends to be a stretching there that beats out the electrostriction. So I think it's an independent effect that's just inherently weaker than this dipole effect here. So now you can see we have this kind of rough alignment here. And now, and again, the preferred way to do this is to make this permanent, to zap it sufficiently strong. You don't have to do that. With just some weaker electric field, you can get these, but then you take it off and they'll go back to being randomly oriented. But with sufficiently strong fields, you can make it permanent, and that's what people do in sonar. Now we have this, a situation now, we've changed this material here. We have a net polarization. And now if we put an oscillating electric field on top of this, whether this is permanent or externally supplied, we modulate it. Now we get what we want. We get a much stronger effect, and it's going to have a nice linear regime here, relationship between the strain and the electric field. And it's reciprocal. Oh, I'm sorry, I didn't tell you something. I missed something important here. Well, it's interesting. I don't know how important it is. This electrostriction, another problem, it's not reciprocal. Which kind of makes sense. You have these randomly oriented dipole moments. If you compress them, you don't get any mechanical you don't get any electrical action. Squeezing them does not produce an electric field. So there's all kinds of reasons why electrostriction is not good for transduction. Now here's something that threw me when I first went through this, and these authors, you know, I guess it's too obvious for them. The material that we're we started off with this ferroelectric material. We've polarized it, usually permanently polarized it. Okay, it's going to behave as a piezoelectric. Technically, it's not a piezoelectric material, but it acts like a piezoelectric material. And so people call it, they use the word piezoelectric. That just caused all kinds of trouble with me, because I was trying to understand this stuff, and you know, they weren't careful with the words here. It wasn't explained. So we will use this. Everyone uses this word piezoelectric. I don't think technically it's correct, but you know, there's no way you can stop it now, and it's reasonable. The material is going to behave like a piezoelectric. Here. It has a polarization axis here, and what's going on transverse there? It's symmetric. We have rotational symmetry. That greatly simplifies things. And we'll see this in a moment. We'll start to see it today in this lecture. Okay. Different ferroelectrics behave differently. Some, if you permanently polarize them, they're fairly permanent. Now, like anything, if you abuse it, they'll start to depolarize. And some of you may be familiar with this on ships and submarines, right? You can, and we'll talk more about this later in the course, but you know what's coming here. If you overdrive it, for example, if you've got a sonar projector and you drive it too hard, you're driving with an electric field and it's vibrating like this, sending out sound, you can start to get depolarization. Temperature is a problem. It turns out that there's a Curie temperature here, just like in magnetic and ferromagnets. And some of these Curie temperatures are not very high, like they are for iron. Iron is way up there, you know, thousands of degrees, I think. It might, no, or maybe it's 700 degrees Celsius. I can't remember. But it's pretty high. But some of these sonar materials that we're going to talk about, they're you know, you go into an ocean where it's, you know, tropical, and so you can get near the Curie temperature. If you get near, it's not, as you increase the temperature here, and you eventually get the, if these are all lined up, and you increase the temperature, which causes agitation, when they break apart, when they don't have the net polarization here, it doesn't happen, it happens approximately abruptly at a certain temperature. But if you're below that temperature and close to it, it can, over time, there can be degradation of the polarization. It tends to be less and less polarized. Depolarizations can start to occur. So that's another problem. Okay. So that's kind of a brief, incomplete introduction to sort of the physics of what's going on here. What we're going to do now is look at the classic sort of first example of piezoelectricity, and that's quartz. And how do we describe? You remember from the last chapter, the way we describe this is we have the strain in terms of the stress is described. We think of this as a drive, and the strain is the response. It's described by this compliance matrix, little s here, which is a symmetric 6x6 matrix. Remember, these are 6-dimensional vectors here for convenience. And here's what the compliance matrix looks like. There are different types of quartz. This is alpha quartz. It looks like this. Now you'll notice here, these are not, you know, these are the same as this. See, those two are the same, but different in the z direction. Oh, universally, the z direction, sorry, let me back up here. So we're talking about a naturally occurring a genuine piezoelectric material, right? The XYZ axes are chosen by convention to be certain directions. And everyone obeys that, okay? You'll notice, if you want to try to understand this, you see that there are zeros here, and there's some symmetry going on here. You'll see S1. This is the same value here as the same value there. So there is an XY symmetry here, but that won't explain all of the zeros and the repeated values. Here's another. It has to be symmetric. This matrix has to be symmetric. But you'll see. See this value is the opposite of that. You know, why is that? Well, it's beyond just XY symmetry here. Let's explain this. So I remember struggling with this, and finally in the end I decided we're not going to try to explain why the zeros are here. You can go some way, but you can't go all the way. But for the material that we're interested in, which are piezoelectric ceramics that have been polarized like I just described to you, there, because we have a nice axis of symmetry, we'll be able to go a long way, I think nearly completely explain the structure of these matrices. Remember, there are three matrices. There's the compliance matrix, that's mechanical. There's the electrical, that's the permittivity matrix, and then there's the coupling, the D matrix. So for right now, it's best not to try to explain this, okay? It's just to postpone it, and we'll begin this. I think today we'll be able to begin explaining it for the piezo ceramics that we're going to spend most of our time working with. The textbook has actually values of these constants. We will be doing some problems throughout the rest of the course where we actually plug in values and come up with real numbers, because that's sort of the bottom line in transduction, right? You want a transducer that works. So going along with that is the fact that we're going to be calculating definite numbers. So there's a lot of constants for different materials in the book. Right. Okay, now it turns out for quartz, look at this. This is nice. It's diagonal. The permittivity matrix is diagonal. Again, this is, you can see the XY symmetry here. It will turn out that for piezo ceramics, we actually have a simpler matrix than this, which is nice to deal with. It turns out we'll be dealing with the same matrix here. It'll have the same structure. Same permittivity constant in the X and Y direction, but different in the Z direction. So the XY symmetry here is that you apply an electric field in the X direction, you tend to cause a polarization, right? If you apply it in the Y direction, the fact that these two are the same means you're going to get the same polarization. Now technically, the quantity that gives you this is the susceptibility. The polarization is proportional to the electric field. The constant is susceptibility. But remember, we have different symbols. They all have the same information content. The permittivity constant, the dielectric susceptibility, and the relative permittivity constant, they all have the same information. Just people use, they're used for convenience, but mainly it's just a historical thing. So this is pretty clear, and we'll talk more about it shortly for the case for the piezo ceramics that we're going to be interested in. All right. So what about the piezoelectric strain matrix? Okay, this is the coupling, right, between the mechanical and the electrical. Remember, it's how the change in strain due to the change in electric field. And you remember, it's not a square matrix, right? So here it is, 3 by 6. And now the first thing you notice here is that there are a lot of zeros. And this is actually, I think, typical of sonar transducing material. You just can't throw something together and assume you're going to have a coupling. You could be hitting one of these, you could be assuming that one of these zeros is not zero. So you have to pay attention to the different directions and be guided by this. So that's actually typical. The next thing you notice is there aren't that many independent quantities here. Look at this. This is D11. This happens to be the opposite of D11. All right? This is D14. This is the opposite. Okay? And what's sitting here, this element, is, minus twice this. So there's actually only 2 independent values here. Again, we want to postpone the understanding of this. We're going to wait until we do the standard material, piezoceramic material. So here are the standard, or the canonical transduction equations for piezoelectricity, dealing with stress and electric field as the independent variables, and strain and displacement field as the dependent variables. And this is, you can see the reciprocity here. It's right there. So this is shorthand. These are all vectors. The capital letters here represent vectors. The lowercase are matrices. You can take these, the particular forms for alpha quartz that we've seen here. You can take this, and then the piezoelectric strain matrix, plug them into here, and generate all specific. This is shorthand for all these equations. Okay, and there's going to be actually, I guess, 12, technically 12 of these. Oh no, excuse me. So there's 6 equations here, 3 equations here. So there's going to be 9 equations. And I can't remember if Brian wrote this out or not, but you know, imagine me going through this for the first time, having no idea what's going on. So I just felt, I wanted to see what this looked like. Okay, so I can't remember if it's in the book or not. It takes up a lot of space. But look at this. God, how do you fathom that? How do you turn this into something useful? How do you get your head around this, or whatever you want to say? How do you deal with this? And I think it's a little bit surprising, because we've got all these nice zeros here. Now, that looks nice. It's just there are a lot other, there's just a lot going on here. These zeros help, but we're still, even with the zeros here, and then a lot of zeros in the piezoelectric strain matrix, we still have this mess here. And it's not what we would call manageable, okay? Now, of course, you can shove it on a computer, but, and I'm sure people, there's no doubt that people do this, that they use computers in the design of sonar devices. But you also want to just develop intuition and be guided by your intuition to get a feel, because the computer is just going to start spewing out possible things that you can do. It may not be convenient, right? You might be able to code that in there somehow, but which sounds like it's starting to border on artificial intelligence. But so it's nice to have some kind of physical feel, okay? So how do we deal with this? Well, before we get into that, there's one thing that's always been a mystery to me that I've never looked into, but if any of you get interested, please let me know. Look at this, and it's not a big deal, but look at this. This is supposed to be little s66 here. So for some reason, little s66 is identical to this. Now I strongly suspect that that's not general. That if you we're talking about this is purely elastic. Forget the electrical stuff right now. This is an elastic issue, theory of elasticity. I doubt if it's a general relationship for any solid. I don't think so. I think it has to do with the quartz having this XY symmetry. But it is interesting that S66 is not an independent quantity here. It turns out, Brian makes no comment about it, but it turns out to be identical to, as a function of S11 and S12. Okay, so even, as I said earlier, even though we have a lot of zeros in those individual matrices there, when you write all the equations, we still have it's huge. It's just unmanageable. So what the natural thing to do here is to look at specific geometry. So we're going to look at an example of this. Here's, so again, this is alpha quartz, and the x-axis has a specific meaning, you just can't choose the x-axis anywhere. You've got to know where the crystal, you know, it refers to the crystalline structure in there. We're going to suppose that it's cut here like this, called an X cut, cut perpendicular to the X-axis. And let's imagine electroding these two faces right here. So we have nice metal here, and we have wire leads connected to it. And so in this case, we're going to have stress-free operation here, except in the one direction. Okay. Now, one thing you'll notice here that causes simplification is, it's interesting. We can put we can change the free charge on here. So we're going to have a D1. We're thinking of this as a driver. Okay, it's reversible here, and I'll talk about that right here. So we want to treat it in general here. But just, I want to make sure you understand, when we treat this as a transmitter, we're going to be putting free charge in, and that argument for no displacement field is gone now, because remember, it's dictated by the free charge. So we'll have a D1. We won't have a D2 and a D3, because there's no free charge transverse here to this direction. So if you look at the equations, with no D2 and no D3, that means there's no electric field in the 3 direction, right? And because we have no stress, we have none of these shear stress, we only have one stress in the one direction, the X direction. You can see that that E2 will have to be equal to 0, because D2 has to be 0. So that's nice. You always want to look for these simplifications, because nobody wants to deal with this unless you absolutely have to, right? And then, like I said, you're going to probably have to shove it on a computer. Okay, so this is going to greatly reduce the equations, but before I state the equations, I want to make sure everyone understands something. We've been through this before, but I think it's good to see it again. This is really the whole point of this course. This thing can act as a source or a receiver in liquids or solids. Oh, what about gases? In principle, it'll work, right? If I oscillate the voltage here, I'm just going to I change the electric field, oscillate the electric field, and I'll be squeezing, and this thing will squeeze and elongate, and it should send out sound. But the big problem is, remember, this is a solid, and it's just not going to, there's not going to be much straining here, or you'll fracture it. So that's a problem. I'm hoping that a racquetball painted with silver paint will have enough. So I think about this all the time, you can tell, right? It'd be great if we can get that demo to work. So we're going to find out. So that's why I said, look, this is just, and you can buy, so I have some, you can buy piezos that will operate in air. They tend to be ultrasonic though. So I've got some that are 40 kilohertz that we might end up, we're going to be using shortly, I think. Okay, so the idea here is that if you drive this with voltage, as I said, this will create sound. Going the other way, if a sound wave comes in here and it's got, you know, compressions and expansions, it'll compress and expand this. That will, by the piezoelectric action, that's going to create an oscillating, change the electric field and therefore change the voltage. So you can use it as a sensor. If you really need sensitivity, you want to operate on resonance, right? Either as a transmitter or a receiver. And to be able to calculate that, deal with it, you need to know the speeds, different speeds of sound, elastic speeds of sound. That's one of the reasons we studied that. Remember at the end of chapter 2 or whatever. And we'll get into that later in the course. Okay, so anyway, here's what the equations now look like. So we started with this mess, and now for this particular example, here's what we've got. We have all these are 0, and this is not too bad. This is what might be considered manageable. Okay? And when you do calculations, as you've already seen, we've done several calculations. Sometimes you don't need all these equations. This is giving you the complete information of what's going on here, but sometimes you don't care. You're after a sensitivity, and you can ignore some of the equations. You don't need, those are detailed information you really don't need to be explicitly aware of. You just work around it. So we've seen examples of that. Now I want to point something out here. we see the piezoelectric action here. The strain in the one direction can be due to, of course, a stress. That's just theory of elasticity. But an electric field. You got an electric field there, or you change the electric field, you're going to cause a strain or a change in the strain. We can see that's the piezoelectric action. And I want to point something else out to you here. Look in the y direction here. Oh, in the z direction, we get a strain. Why are we getting a strain? That's the 2 words. What do we call it? Why are we getting a strain in the z direction when we stress it in the x direction? 2 words. First word starts with a P. French person's name. Yeah, Poisson's ratio, right? So we just call it Poisson's ratio effect. I guess we should say effect. So this is the pure Poisson's ratio effect. Okay? Now look at this. And this is really coming from our canonical equations, but from a physical point of view, it needs to be pointed out. I need to point this out to you. This is a Poisson's ratio kind of thing here. Okay, it's purely elastic. But we can see that an electric field in the x direction here, which we're going to have in general, right? In our geometry, it can cause a strain. And it's not doing it through here. You know, it is causing an S1 strain. Now there's no Poisson's ratio here. So this is a Poisson's ratio effect, but it's associated with the piezoelectricity. It's independent of the Poisson's ratio effect here. So I usually call it it's a Poisson's ratio type effect associated with the electric field here. So it's more than just Poisson's ratio is operating here. We also have another term there. I want to make sure you see that, because this will come up again later in the course. Oh, here's another thing. It's kind of surprising, but this is not simple material. We've got a shear of what plane? Okay, 4 is associated with x, yz plane. So this is a shear of the yz plane. So it's going like this or like this. Where did that come from? Well, it looks like symmetry would preclude it. Well, quartz is not that simple. It's not, okay. We're not going to have to worry about that for piezoceramics, which is nice. But it's there, and it causes trouble. And clever people have found a way around it. Okay, so they've probably done this they probably used to do it for watches. I'm sure there's still watches out there, right? We need, yes. What?
They definitely exist.
Yeah.
I think they're more decorative these days.
But people are going to still use quartz for accurate timekeeping. So what's in a mobile phone? Oh, that gets time. It's time off of GPS. Huh. Okay. Well, anyway, clever people found a way of cutting this to kill that, somehow kill any shearing, because it evidently was causing trouble. You can see that, you could guess that it probably could here. So I don't know if this came about for timekeeping purpose. I don't know what the history is, but it's mentioned in Brian's book or somebody's book. I doubt if Brian would have. I probably found this in another book, but I can't remember. It doesn't matter. You can actually kill that if you cut it, if you're creative, cut it in some kind of weird way. That's probably not obvious. Okay, so we have very little time here, but that's okay. I just want to start this. Now we're going to get into the stuff that we really care about. Okay, it's called piezoelectric ceramics, and I'm going to add here what everybody in the world calls it. This is too many syllables, so we call them piezoceramics. That's the shorthand thing. And you might find this interesting. The ceramics go way back, right? Tens of thousands of years. And it's still not a perfectly scientific process. People don't know. And you can try to do the same thing twice, and the product will not be the same. It'll be different. And people don't really know what's going on there. So it has this kind of, you can think of it as, it's not purely science, you can think of it as kind of art, okay? That still exists in piezo ceramics for sonar material. There's not high reproducibility. There's sensitivity to little things that people just don't know. So that caused a little bit of trouble. Well, and it's been quantified. This is so important, right? The nuclear warheads on submarines thing. That it's all been kind of quantified, and we'll talk about that later in the course. So what these are is ferroelectric materials that have been there. When you cook them up, the polarization, the domains are randomly polarized, and then you hit them with a very large electric field. How do you do that? Well, the natural way to think about it is you electrode it, which you're eventually going to have to do anyway to make them a useful transducer. You electrode them and then you zap them with a very strong electric field and produce the polarization. So this is, I believe, what is routinely done. You can imagine permanent polarization this way and electroding this way. It turns out that I've never seen that. And if you start to do I did some simple calculations once, it just doesn't appear to be useful. Okay? So the polarization will, as far as I know, is always in the direction of the electroding. And it's reasonable from a manufacturing point of view, because how are you going to zap it with a strong electric field? The natural thing is to use the plating, electroplatings that you're eventually going to need anyway. So it makes sense. Now, everybody, there's one slight exception, don't worry about it now, but by the convention here, very strong convention, is the z-axis is the direction of polarization. We call that the z-axis. That's something you can count on. There's one slight problem that we'll see later on with the geometry of hydrophones, but it's not a big deal. Okay, so we'll pick this up from here, and we'll look at this physically. We'll get a physical appreciation for the three matrices that we're going to be dealing with for piezo ceramics.
There's like 60 minutes.